Okay, welcome to lecture 11 of submodular functions optimization and applications to machine learning. Today is going to be another interesting lecture. We're not going to do quite as many theorems as last time, although we are going to do some theorems, but not as many, and we're going to see some more examples. So let's get right to it. I guess the title of this lecture is maybe more properties of polymatroids and, interestingly enough, special cases of submodular function minimization, which we will initially see in disguise. But before we do so, let's just do a little bit of review. So last time what we did do is prove this really, really critically important theorem, which shows that the vector rank function for a given x, which is defined based on this, is basically equal to the following submodular function minimization problem here, which does a number of things. For example, it allows us to show that essentially a polymatroidal polytope and a polymatroid are the same thing, and they correspond to a polymatroid function, and moreover to show that any polymatroid, any sort of geometric shape in n dimensions that's a polymatroid has an associated submodular function, and vice versa. And so basically all submodular functions are characterized by that polymatroid. And so that basically says that the polymatroid, or the polyhedral polytope, is everything about the submodular function. Yet it has some very, very special characteristics, which we will try today to sort of gain some further geometric intuition about, in particular with regard to like the greedy algorithm. And we're going to see, in fact, that the greedy algorithm, interestingly enough, just like in the Matroid case, so we saw in the Matroid case that the greedy algorithm was something that characterized the Matroid. Well, we're going to see that the greedy algorithm, corresponding to a sort of a polytope in Rn, being optimal, also characterizes polymatroid functions. So therefore, submodular functions, or their normalized brethren, which is basically the polymatroid functions, are exactly identical to those polytopes for which the greedy algorithm is optimal. So, interestingly enough, that characteristic of matroids also generalizes. And that's what our goal is. Our goal is for today. So also last time, slightly better notation, because we had some good questions on this, about what the join and the meet are for vectors. And so here's a slightly improved version of that slide, where, as you can see, the parentheses are matched, right? And so on and so forth. But basically, it's the max and the min of each vector. Okay, and based on that, we saw that, and we proved, which was a surprisingly involved proof to show this. But I think if you go back and look at the lecture, and you'll see the geometry, that the rank function, the vector rank function, is submodular in the following sense. Okay, and also the other theorem that we proved was that for any polymatroid, there's a polymatroid function f such that p is equal to pf plus. Okay, so the stuff that I just highlighted in yellow is really the statement of the theorem without all of the red clarification. Okay, a couple of other things that we defined, which are very important. D of y, which is the lattice of tight sets. And the reason why it's a lattice is because it's closed in a union and intersection. And we also defined the one element of that lattice, which is the sat function, or in some sense the closure function, and we will see it again in the context of today's lecture. Okay, so we're going to start with some any questions on review before we continue. Tenji, you look like you have a question. No, you understand everything. So in fact, I'm really tired. Can you please come up and lecture for me? I'm going to sit down. No, I'm kidding. I'm kidding. Actually, I'm not kidding. I am kidding, but I'm not. I'm half kidding. Recall how a matroid, so this is just a very simple notational slide that we can say that a matroid can be defined based on a ground set and a rank function. So sometimes in the literature you will see that a polymatroid is defined either based on a ground set and a polymatroid function, or alternatively you might see that, I think I have this on the next slide, I can't remember, but sometimes you'll see that it's defined as E and then some polytope, P. Okay, so all of these things are essentially equivalent now, and so when you say given a polymatroid E comma F or E comma P, you see that all makes sense. Those are all sensible things to do. Now the other thing is that, remember the theorem, the right-hand side of Theorem 9.4.5, which was one of the critical theorems that we proved. It was this thing that which we said was basically a submodular function minimization problem. And what we want to do is, in this course, sort of get an idea of some of the flavor of submodular function minimization algorithms, the combinatorial ones and also some other ones. And what we're going to do is, by looking at special cases of it first and looking at it a little bit historically, we'll gain some intuition as to the kinds of things that one does when one wants to combinatorially minimize such a function. So remember we said that this basically, corresponded to any general, I think I have that on the next slide, this corresponds to general submodular function minimization, right? Because those two yellow things are identical, right? And then, since we know that we can take a polymatroid function and subtract off if we can subtract off any modular function from a polymatroid function, we have all possible submodular functions. So that thing, this thing in the bottom here, is general purpose submodular function minimization, right? It's as general as it gets. So we need to solve this. And we have an interesting duality theorem associated with that. We have a maximization problem whose dual is this submodular function, this general purpose submodular function minimization problem. And so that's going to help us. This is another slide that we saw a variant of before, and this isn't really that critical, but I just want to mention it briefly that you can also define, given an integral polymatroid function, you can also define a matroid. Okay. And I'm going to leave that as an exercise for the homework, the next homework. Now, another thing that may be worth mentioning in passing is that we can look at Theorem 9.4.5 in the matroid case. And so in the matroid case, basically all we do is we're saying that this minimization problem, in the special case where where the function f is a matroid rank function, has as its dual this maximum independent, so this maximum vector rank problem, but where the polytope here is the independent set polytope. So remember, the independent set polytope was the convex hull of the characteristic vectors of the independent elements of the matroid. So that is the special case in the matroid case. Okay, so those are just things I wanted to point out. Now, are there any questions? Okay, so if there are questions, now this is a good time to ask them. So what we first want to talk about is define this notion of most violated inequality, because sometimes, that is essentially the submodular minimization problem. So we've got this polytope. Here it's shown in the matroid rank case, PR plus. And we saw that those two polytopes were the same, namely the convex hull of the incidence vectors and then the PR plus. So if it's the case that we've got some x that's not in this polytope, okay, so we've got an x which is in the non-negative orthant and it's not in the polytope. What does that mean? So it's not in this polytope here. So by not being in the polytope, so this part is fine, right, because it's in the positive orthant. By not being in the polytope, it must mean that one of these inequalities has to be, one or more of these inequalities has to be violated. At least one has to be violated. Okay? Because everything in the polytope has to be has to be feasible with respect to those inequalities. And so the idea of the most violated inequality, the one that's most violated, is the one, how can you say an inequality is most violated? And we sort of rank, order, or sort of judge the inequality, the violation of the inequality by its margin. And so we can say that if we were to, for example, find an A that maximizes this quantity, okay? So in other words, if we do this problem here, and we find that A, then that's going to be the most violated inequality, right? That A. And you know that A is going to be positive. The A is going to be, the solution to that is going to make x of A minus r of A positive, because we know that x is not in there, right? There is at least one A such that the inequality is not true. So that this maximization problem then corresponds exactly to this minimization problem, right? Because to max that, we min the opposite, and then we add back in x of e, which is a constant with respect to the minimization, which is exactly the right-hand side of theorem 9 point, whatever it was, 9.4.5 or something. And that's, again, that satisfies, that comes back from the modularity. And so the most violated inequality problem is obtained by this minimization, which, as we said, this minimization is really just a special case. In the Matroid case, it's a special case. In the polymatroid case, if it wasn't a Matroid rank function, it was a polymatroid function, it would be a general purpose submodular function minimization problem. Now, in general, if you've got a set of, especially an exponential set of inequalities, but even, in general, testing membership in a polytope is a hard problem. But what this is saying is that if we can solve submodular function minimization, that for this particular class of polytopes, the polymatroidal polytopes, there's a polynomial time solution for doing membership testing. Because basically, to see whether x, we pick a particular x here, and to see whether it's in the polytope, it's a non-negative orthant, so that's fine. We can easily check that if all of the elements are non-negative. But to check whether or not it's in this polytope defined by the set of exponential constraints, in general, you can't do that. That's one of the classic grand open problems in mathematical programming. But in the polymatroidal case, you can do this. It's easy in the sense of it's as easy as submodular function minimization. So if we can solve submodular function minimization, which for a long time, people were thinking about this problem maybe for 15, 20 years, starting in the early 60s and culminating in the late 70s, answering that question affirmatively that yes, there is a polynomial time algorithm for general purpose submodular function minimization. And we'll review that algorithm in a couple of lectures. But this sort of solves an interesting problem. So, I mean, why is this important? So in machine learning in particular, this is speculation now on my part, but many people will have developed, for example, like approximate inference strategies for graphical models using things like the marginal polytope. Like you might have essentially a graphical model, and you might have essentially a polytope defined on the potential functions, and essentially a set of constraints on the potential functions which are defined by consistency along, say, edges. And you might, for example, take an outer bound on the polytope by saying that you only have a subtree or something, and then you only have a tree consistency, which gives you a sort of a tree consistency on the marginals of a graphical model, which if the true graphical model is a tree, are correct. Now, other types of outer bounds might be solvable if they're maybe polymatroidal. So there might be some strategy of using polymatroidal outer or inner bounds of a polytope. And if that polytope is nice, you could find a solution in that polytope where if you can show that the solution is bounded within the polytope, it's good. So in other words, to do outer and inner bound polyhedral approximation, you need to, first of all, show that the outer or inner bound is in fact a bound. B, have an outer or inner bound that's easy to work with. And C, that if you use the outer or inner bound, it's useful. In other words, it's not so bad. And so what we have here, from the perspective of a potential machine learning application, is the second condition of those three conditions being true. Namely, as we will see more evidence of, this is still a fairly flexible polytope, and it's easy to work with, as you'll see. Okay, so. The problem we're going to solve in particular is we're going to have a matroid. We're going to do this in the matroid case first. And we're going to take a vector, x, a non-negative vector, and we're going to find a maximizing y in the independent set. So, in other words, a p basis of x. And we're going to express y as a convex combination of incidence vectors of the independent sets in the matroid. And also we're going to return a set A that satisfies this inequality, the right-hand side, tightly. Now by theorem 9.4.5, we know that if y is a p basis, then all x are going to satisfy that with as an inequality. But we're going to find one here where it's an actual equality. Okay, so this one, which I'm about to unhighlight or highlight in yellow. Moreover, because of the strong duality-like notion there that we've got, the existence of that A will certify that, on the one hand, Y is a maximal independent subvector. So in other words, it's a P basis of the matroidal polytope, and A is minimal. In other words, it's the most violated. So A is the solution to this special case submodular function minimization problem. Now, it's already pretty. You might think that this is. We gave a flavor of how flexible matroids are and matroid rank functions are earlier in the course. And so what in some sense we're doing is we're solving a special case of submodular function minimization to the extent that we're dealing with a matroid rank function. But still matroid rank functions have very, very rich dependence structure. So in some sense the dependency-like structure in a matroid rank is as rich as any polymatroid function. What is different about the polymatroid and the matroid rank function is that the polymatroid function has this sort of notion of partial dependence, as we saw. And we also saw the notion of the partial dependence in the polyhedral structure. So remember, the matroid polytopes all kind of look like this in 2D. Right? It's either a point, a triangle, or a square. Whereas the polymatroid polytopes have these sort of partial dependencies. And partial, because we have, these sections. So it's in other words, we don't have necessarily this part in the polytope. So it's partial dependency. And why is partial dependency? We will see that a little bit more in the future. But that's the difference. Okay. So we're doing this case here. But we're still allowing ourselves to subtract off an arbitrary x. Okay, so there's no constraints on x. Like it doesn't have to be integral, it doesn't have to be an arbitrary non-negative x, that is. And so this is also going to be a membership, a special case of the membership test, because it's going to test whether or not the sign of f, the sign of f is going to be, because since that's going to be the minimal one, the most violated one. So what would the sign of f tell us? So in other words, if it's the case that we minimize this function here, so if the sign of f is positive, if the sign of that resulting f is positive, then what does it mean? So that's the minimal one and it's still positive, so it means that f is greater than x, or x is less than f, so it means it's not violated. Whereas if the sign of f is negative, it means that there's a violation. Okay? So the sign tells us whether or not x is in the polytope or not. And also everything runs in polynomial time. So the algorithm, which we're not actually going to describe in detail today, but I just want to give you the idea of the algorithm, because we need to, all of these other bullet points up at the top of the slides, we're going to need to go through all of that before we actually get to the details of the algorithm. But here's essentially the essence of the algorithm, which I want to give first. So we build Y from the ground up, and we essentially keep a set J of independent sets of the matroid. And each independent set of the matroid has a coefficient, lambda, and it's convex combinations of characteristic vectors of the independent sets of the matroid. And so convex combination means that the lambdas are non-negative and sum to 1. And moreover, the Y is this convex combination of the independent characteristics vectors of the independent sets of the matroid. And we're going to build Y up by adding new independent sets. So we're going to augment J, adding to the existing independent sets and adjusting coefficients. So basically we're going to add an independent set, and then we're going to get a non-convex combination, and then we're going to adjust the coefficients to recover convex combination, the quality of convex combinations. Okay? And each one of these additions is done using a simple max flow algorithm in an associated graph. So we're still going to use max flow as a subroutine, but we're going to build a data structure in some sense from the submodular function, from properties of the submodular function, or the matroid function in particular. We're going to build a data structure and run it multiple times. So it's interesting that max flow and min cut is a special case of submodular function minimization. So we're going to use this special case and obviously call it a polynomial number of times. And each update will ensure that after we do the coefficient adjustment, we'll make sure that we stay within the independent polytope, and we'll also keep this true, namely the subvector property. And so like I said, it's going to take us, I don't know how many lectures, a few lectures. That's sort of that's an insurance policy to use few as opposed to saying one lecture. So let's just keep it at few. And but this is our goal for the next lecture or two. Okay? So any questions on the goal to sort of develop this algorithm, which we won't actually see again probably until definitely until next week. So if you're wondering why are we doing all this stuff, if you have that question like a half an hour from now, go back to page 34 or frame 16 of the slides and remind yourself. Okay, so any question about why we're doing what we're doing? Why we're doing it? Because it's a special case of submodular function minimization, which is actually simpler than the more general case. What we're doing is developing the tools to give us this algorithm, which is, by the way, Jack Advance's algorithm. This is why I like to say that he's the one who sort of developed the first special case instance of submodular function minimization. Okay, so this is a digression, but it's not really a digression at all. Okay, so harken back to the days of undergraduate computer science when one was studying for the first time algorithms and bipartite matchings. Or actually, no, I should say, remember in junior high school, remember in grammar school when you were learning about long division, bipartite matching, polyhedral polytopes, all of those things were together. And we defined a bipartite graph where we've got a left node, set of left nodes and the right nodes, and we have a matching. Right? So a matching, what is a matching? It's a subset of edges such that for any vertex is incident to only one of the edges in the matching. It's a subset of the edges. So, and we can say that a node or vertex is matched if it's the case that the set of nodes in the matching. So the matching nodes are A. So are A here. A is a matching. It's a subset of edges, and we say that a vertex is matched if one of the edges in A is incident to that vertex. And otherwise, it's called unmatched. Right? This is called the heterosexual matching problem. There's also a homosexual matching problem as well, but this is the heterosexual version. The homosexual one turns out to have a different structure, but we're not talking about that one right here. But actually, it's very funny because if you go back to Gene Lawler's book, he actually addresses these two matchings with those particular terms, which was, I think, extraordinarily progressive given that book was written in the 1970s. But he was in Berkeley, and everybody in Berkeley is very progressive, even in the 70s. There's actually a story about Eugene Lawler, by the way, which I shouldn't tell on YouTube, but I will, that he was a great theoretical computer scientist, but he was also a hardcore 1960s Berkeleyite who was arrested in a protest in the late 60s. And Richard Karp, does everybody know who Richard Karp is? Richard Karp is the father of, he's the one in the 1970s who wrote that classic paper on the irreducibility of polynomial time algorithms showing the first 21 problems are NP complete. He's a Turing Award winner. He's very famous. Everybody should know the name of Richard Karp. But anyway, Richard Karp went to the jail and bailed out Eugene Lawler. This famous Turing Award winner computer scientist. Who I greatly respect both of them. They're both extraordinarily nice people. I had the pleasure of knowing Eugene Lawler back when I was an undergraduate at Berkeley, which at the time I had no clue he was working on any of this stuff, by the way, which is it's kind of amazing. But none of this stuff is relevant for YouTube. But anyway, let's talk about alternating paths. So basically, so we've got matchings, and an alternating path is basically it's an undirected path of unique edges that are alternating in the matching and out of the matching. Okay, so basically, you've got a set of matched edges, I'll show you some examples in a minute. We've got some nice graphic examples. Basically, we've got a matching which is a subset of edges. And then if you have a sequence of edges where maybe the first edge is in the matching and the second one's not, and the third one's in and out and in and out. So basically it's just a set of edges that alternate between being a part of the matching and being not part of the matching. And so let's just define S1/2 is basically S except for A. So this is essentially, it's either the odd or the even elements of S. Okay? Okay. And now the notion of an augmenting path, which is distinct, it's an alternating path between two unmatched vertices. So in other words, if you start with an edge that whose first incident vertex is unmatched and second incident vertex is matched, then since it's an alternating path, the next vertex corresponds to that's matched, and then you keep going back and forth until the final edge is between a matched vertex and an unmatched vertex. That's called an augmenting path. And yes, I do have a figure giving exactly this definition, if that's what your question is. Is that your question? No, question. Yeah, okay. So we can increase the matching if we find an augmenting path, as I will show you. And give you an intuition. And so basically the updated matching becomes the symmetric difference. A prime is the new matching, which is A symmetric difference S, which is really just A except for S union together with S except for A. We're just unioning those two things together. Okay? And so we have this alternating path bipartite matching algorithm. So we have a bipartite graph G. And let's start with an arbitrary matching, which could include the empty set, because the empty set is a matching too, right? And then this algorithm says that while there's an augmenting path, S and G, sort of replace the matching with the matching symmetric difference with S, which when A is empty, when we start with the empty set, it's just an assignment to the alternating path, to the augmenting path. I'm sorry if I keep saying what I mean is augmenting path there. So remember, the alternating path just goes back and forth. The augmenting path is an alternating path that insists upon the two n vertices being unmatched. Now this can be easily made to run in m squared n time, where m is the number of edges and n is the number of vertices, which is clearly polynomial time, and also it can be made to run a lot faster. Now the critical thing we need to say is that it is polynomial time. There are a number of different algorithms for this that can be made to run faster, and also it depends on, in some sense, how big n is and how big n is, and so on and so forth. Like sometimes you can do like n squared times square root of m, and there are different variants of the algorithm that you'd want to use depending on the sparsity pattern of your graph. It's like a no free lunch kind of thing. Okay, so here's an example. And then just to make sure, so here's a bipartite graph. We've got 5 vertices on both sides. So V is the left set and F is the right set. And any edge is an augmenting path, right? Because it joins two unmatched vertices. So let's just take 2, 7. So that's an augmenting path. And if we then replace the empty set with the red edge, then that's a matching. Is it a maximum matching? No, but it's a matching. So any edge that's not intersecting nodes that are adjacent to the current matching is also an augmenting path. Why? Because again, its ends are between two unmatched vertices. So like 3, 8 is between two unmatched vertices, right? 4, 10 is also between two unmatched vertices. Now, are there any single edge augmenting paths left after this point? No, because basically any vertex that we choose, or any edge incident to any vertex which is not part of this matching, it's not a max matching, but it's kind of like this is showing that the greedy algorithm doesn't work, right? So you run the greedy algorithm, you keep finding an augmenting path, but then you get stuck, right? So somehow you stop, and you can't do. Remember, the greedy algorithm only adds; it never removes. Right? So this is not the greedy algorithm. We've used the greedy algorithm up to this point, but it's no longer the case that any edge addition will work. And this is not a maximum matching. The goal is to try to find the matching that has the greatest number of edges in it, or the maximum weight matching if this was a weighted case. But we're talking about the unweighted case. So, but what we can do is take recourse in the idea of augmenting paths. But yeah, question.
So I have a question about augmenting path.
Not long division? So, no. I probably wouldn't be able to answer that question about long division.
So does augmenting part depend upon the actual matching set which you have selected? So it's possible that an edge is a part of an augmenting path?
The augmenting path absolutely depends on the current matching. Remember, it's augmenting relative to the current matching. So each one of these additional edge additions we're augmenting with respect to the current matching, because it basically says, I mean, obviously, so when we say an augmenting path, it has to be between two unmatched vertices. So there has to be some, relative to some matching, right? Since you have a different matching, those vertices might not any longer be unmatched.
So it's not related to just the maximal.
The augmenting path is relative to a current matching, which might include a max matching, might include a non-max matching. So does everybody see why there's if we added any additional edge, it's not a matching anymore? Raise your hand if you see that. Okay, but an augmenting path is the following. So we're going to get used to this red, green, blue color coding thing, because we're going to use this in a number of contexts, including a much more complicated context than bipartite matching. So get used to the idea that red is the existing matching, and then blue-green corresponds to an augmenting path, what we will generalize to something called an augmenting sequence, where blue is in the current matching and green is not in the current matching. Okay? So in this particular case, we've got an augmenting path. I can use our new gray highlight color, which says it starts at 5. Because 5 is unmatched, it goes to 8. So 8 to 3 is matched, but then it ends in 9. Right? And that's an augmenting path because the two end vertices, namely 5 and 9, are unmatched. It's an augmenting path. It's also an alternating path. An alternating path wouldn't be one that ends in an unmatched vertex. Right? Can anyone suggest an alternating that's not an augmenting path? So here's one. If we were to turn, let's see if I can do this in real time here. So green is new and blue. So that would be an alternating but not an augmenting path. And why? It's because while this vertex is unmatched, this one is already. So that's not an augmenting path, that's an alternating path. Everybody see the difference? Okay. Okay, but let's go back to this one now. This is the one that we care about. This is the augmenting path. Let's go back to that one. And that one, then we just say, oh, well, let's out with the blue, in with the green. Okay? We remove the blue, add the green, and because of the augmenting property, what we've got now is a matching, and thanks to the fact that it's an odd length augmenting path, we've got a matching that's bigger. So it's like a pseudo semi-greedy step, but it's got a strange kind of backtracking, because what we're backtracking is removing all of the elements in all of the odd positioned elements in the matching according to the augmenting path. Okay? So now we can do again. Here's a more complicated one. But this alternating path is not augmenting. So first of all, why is it an alternating path? because it starts with an unmatched vertex. So here's an unmatched vertex there. And then we start the path with the green guy, but he's unmatched. But then this one is matched. This one is already matched, this red one down here. And there's nothing we can do once we get to 4, element 4. Right? It's gone. So, and in fact, I'll leave it as an exercise to show that starting from this graph, no further augmenting paths are possible. And the theorem that in bipartite matching states that that the condition of a maximum cardinality matching is the same as the condition of there exists no augmenting path. So what this means is that in this bipartite graph, the maximum cardinality matching is of size 4.
Wait, does the definition of augmenting path include the fact that it's like inclusion-wise maximal? Because otherwise it would just end early. Right, I think it's ended at 5 instead of 10 instead of 4.
Sorry, here's the augmenting path. So the augmenting path has to be between 2 unmatched vertices. And the point I'm saying is that in this graph here, there's no augmenting path, because if you take any such path, you're going to you can be alternating. There are alternating paths, but there's no augmenting paths because there's none between unmatched vertices. Okay, and you can sort of like try some paths, and you'll see that no matter what you do, it will be the case that on one end of the path you'll always reach an already matched vertex. But that's a condition that you can use to define an algorithm to find the max matching by repeatedly finding augmenting paths. Okay, and that's something that we can do. And that's similar to the generalization of what we're going to generalize that for the submodular function special case. This is like a variant of what's called the Hungarian method, where you add stuff, but then when you continue forward, you come up with an alternating sequence. We're going to turn alternating path into alternating sequence because the structures we're going to be dealing with are no longer necessarily graphical, but one can still talk about sequences of items that alternate between having one property and not having that property. Okay, let's do a little bit of review. So the next slide is from lecture 7, and then the one afterward is from lecture 5. I'd like to tell you where these slides come from. So here's from lecture 7 again, which is Matroid Intersection, which basically says the problem we defined was taking 2 matroids, M1 and M2, and we look at they're over the same ground set, and we take the common independent sets, right, I1 and I2, and it is easy to show. Actually, this wasn't on the first homework, right? So this will be still on your second homework. So maybe you've already solved this problem. Those of you who are anticipating the next homework and want to get a head start on it have already solved this problem. I'm sure all of you have done this, right? In fact, I'm not even going to ask you to raise your hand since I know you've all solved it. But here is take out your notes from your notes the example where this is not a matroid. And but still, it makes sense to why we might want to find the maximum independent set in both matroids. Or in other words, the maximum cardinality set that's independent in both matroids. And we saw that we can compute the size of the maximal set, and we also defined the convolution of 2 submodular functions, which in general doesn't preserve submodularity, but this was interesting in its own light. And then secondly, we also defined a partition matroid. So everybody hopefully remembers what a partition matroid is, where we take a ground set and partition it into blocks, and then we put a score associated with every block, and you're independent as long as you're not intersecting each block. The intersection of each block is no more than that score, which is Ki. Ki is the score of the ith block. Okay, any questions on partition matroids or on Matroid intersection? Now the question you might ask, and this is a fun example that maybe you've never seen before. So everybody knows what the traveling salesperson problem is, right? So we'll get to that, and what Hamiltonian cycles are. So basically, why would you want to do Matroid intersection? So let's consider this bipartite graph. And Wenwu, please pay attention to this because this is very important for you. So let's consider a bipartite graph. And you define two partition matroids, M, V, and MF, based on the edge set. So it's the same ground set, which is the edge set of the bipartite graph. And you have two independent sets, one based on the left vertices and the other based on the right vertex set. And so maybe I should just draw an example. So here's essentially a set of nodes. Bipartite graph on the left, bipartite graph on the right. The edge set is in green, say. Okay. So we can partition the edges in two different ways. So one partition can be based on the left vertices. So that means that this is the partition. The yellow edges, the green edges, the blue edges, or the orange edges, right? Or alternatively, we can partition it. So this is partition based on it's a partition based on the left vertices, right? Vertices, right? And then we can also partition it, we can do the same thing. So let's draw another bipartite graph here. The same one, which I should have copied from before. So we can partition it based on the right vertices. There's the yellow partition, the yellow block of the partition, the orange block of the partition, which is a pretty big block, and maybe the red block. Okay, so there's two partitions of the set of vertices, right? Okay, everybody clear on that? Two separate partitions. And therefore, since we're defining a partition matroid, we can define a partition matroid based on either one of these partitions, the left vertex partition or the right vertex partition. There's two separate matroids. And here's the left one. So remember the bipartite graph, here's V and here's F. Here's V and F again. We can define a partition based on the left vertices, which is this here, or based on the right vertices, which is this one, right? And we can define a partition matroid based on that. So based on the partition, what does it mean to be independent according to the left one? Basically, it's a partition matroid where the score in each block is 1. So basically, it says that in each block of the partition, you're independent if you only have one of those edges. And on the right, and so basically it's kind of like saying, remember, matching is such that every node can be incident to only one edges. So being independent on the first matroid says that you're sort of cool on the left side, and being independent on the second matroid means you're sort of cool on the right side. And so if you're independent in both, what must that mean? That you're a matching. Right? So matroid, intersection of two matroids gives us bipartite matching. Now, this is not surprising because we said that the greedy algorithm doesn't solve bipartite matching. The greedy algorithm will only get you so far, and then it stops. Right? You need to start using augmenting paths to truly get the maximum matching. Now that doesn't mean that it's not polynomial time. It's still polynomial time, but the greedy algorithm has failed us. But then the intersection of two matroids we know also not to be a matroid. Okay, everybody get it? Everybody see what we're talking about? Okay, so now interestingly enough, do I have this example here? Hold on, let me just see where we're going with this. Okay. This is just another example of two matroid intersections. So another thing we could do is like we could have two graphs, G1 and G2, and we define two cycle matroids on each one of the graphs. And so the matroid intersection problem would be, for example, like, the maximum spanning tree says, sorry, let me just make sure this is very clear to you. So we have two graphs on different vertex sets, but the same edge set. So it's the same set of edges, but the edge in one graph can be very, very different edge in another graph. So the only constraint really is that the number of edges are the same, but they can be completely different edges since there's different vertex set. Like I could do a crazy example. I mean, I have a better example in a minute, but let's say I have one graph which has four vertices, A, B, with four edges, A, B, C, D, and another graph which has them all between the same two vertices. Same edge set, different vertex set. So it's two graphs with the same edge set, different vertex set, and we define two cycle matroids on these two graphic matroids. Yep.
Isn't the endpoint of the edges intrinsic to the edge itself? So all four of those edges connected to the same vertex in the same graph and the first.
Yeah.
So it doesn't seem like those edge sets are the same.
Yeah. So what do we really mean by that? So the question was that don't you normally define an edge in terms of a pair of vertices? And if it's not even the same vertex set, how do you define the same set? So yes, relative to a particular graph, that's a valid thing to do, right? Because every edge is a pair of vertices, and in a hypergraph, every edge is a collection of vertices. But obviously, if it's not the same vertex set, you can't have the same edges. What we really mean is that there's an isomorphism between the two, that there's a one-to-one mapping between the edge sets. Okay, that's the more precise meaning of what I'm saying. I mean, it's the same number and then they have the same set of names, and the names are unique or something. That's really what we mean.
Think of it being like indexed by the same set?
They're indexed by the same set, where the index set corresponds to its name, to the name set, for example. There's nothing wrong with having an integer as a name. I always like the number 17, and if you'd like to call me Professor 17, that's fine. Now the problem and the application might be that we want to find, in the case of one cycle matroid, we want to find the maximum spanning tree. But here, what we want to do is find the maximal spanning tree in both. That's simultaneously a spanning tree in both. So that would be the matching-like problem, but on two graphic matroids, which you can imagine being useful. I mean, it's a useful combinatorial problem, and which turns out to be polynomial time. Now here's an example which is very interesting, might be interesting to you. This is what if you wanted to do the intersection of more than two matroids? Let's do the intersection of three matroids. So first of all, what is a Hamiltonian cycle? We've got a graph, and you have a Hamiltonian cycle. It's defined as basically a cycle which passes through every vertex exactly once. And so this is like the traveling salesman problem where you've got a directed path, and you have a salesman which goes between cities, and you have roads between cities, and it's directed. And it could be the case that a road is labeled with both direction of edges, but you want the salesman to go to visit each city once in an efficient strategy, so that you don't want them to visit the same city more than once. God forbid, So the goal is to find such a Hamiltonian cycle. So now let's take this graph G. So G is the original graph here. Let's take it and modify it a little bit. So, like for example, if this is the graph G, then we'd modify it. We'd designate a special node, and we'd break the node. Let's say that there's directions on the edges, or something, and we'd modify it so that one node, let's say this node here, would become special. Actually, this is let's add another edge here. So you can go backwards. And so the special node becomes two nodes now. And it's the same graph otherwise for any of the vertices or any of the nodes that haven't become two. But basically we've got a special out guy and a special in guy. So in other words, mathematically what we're doing is we create a graph G prime with n plus 1 vertices. And any vertex, let's call this guy V1, so that means that this one here is V1 here, down there, right? That was down here. That's V1, and we break it into V1 plus and V1 minus. And the outgoing guys goes from V1 plus, and the incoming goes to V1 minus. Okay? Everybody, any question on that? So now let's define some matroids on this new graph here. So we've got this new graph. So basically, you can see that a traveling, Hamiltonian cycle exists in the new graph if it's the case that we can start from V1 plus, go around the graph, and then end up in V1 minus. Right? It's an equivalent condition. Right? Because if a Hamiltonian cycle exists, then we would start at V1 and end at V1. Here we're just sort of breaking it into two things, sort of a directed graph. Now let's define a bunch of matroids on this new graph. Let's say M1 be the cycle matroid on G prime on the new graph. So basically it means that you can't have any directed cycles. Let's say M2 being the partition matroid, where we partition the outgoing edges of every vertex. Okay, so every set of outgoing edges from a vertex is one block of the partition, and it's a one partition matroid. So it basically says that you're independent if it's the case that you choose at most one edge outgoing from every vertex. Okay. And then M3 is sort of the opposite. It says, okay, let's partition the matroid based on the incoming edges of the vertex. And you're independent, it's a one partition matroid, so you're independent if and only if you have at most one edge incoming to each vertex. So now what if we take the intersection of these three matroids? Well, it's a cycle-free path that for every vertex has got one incoming edge and one outgoing edge, and it's maximal. Okay, so what does that mean? It means that there's a Hamiltonian cycle if and only if there's an n-element intersection of these three matroids. Which must mean that suddenly what happens is if we want to intersect three matroids, it becomes an NP-complete problem, because the Hamiltonian cycle problem is NP-complete. So three matroids is hard. Something strange has happened moving from two matroids to three. So that's kind of interesting. But we can do two matroids. So that's already said. There's a TSP, the traveling salesman problem is NP-complete. So we can't solve the n matroid intersection problem. But what we can do, we saw this bipartite graph case that we're going to see that we're going to be able to do it for two matroids. Okay. So remember, this is from lecture 5. Remember the definition of a matroid in terms of its circuits. And basically, we're saying that C is the connection of circuits. These are the minimal dependent sets. In other words, they're dependent, but if we remove any element, it's independent again. It's not necessarily a base, so don't get that mixed up with bases. Circuit, if we remove an element from a circuit, it's not necessarily a base, but if we remove any element from a circuit, it's necessarily an independent set. And we can define a matroid based on its set of circuits. And property 2 is the critical one that we want to review. which says that we can do the following thing. If we've got two circuits, say C1 and C2, and remember this picture that we drew? Let's say here's C1, which is a let's just use the graphic matroid as an example. Whoops. Circuit C1, or sorry, C and C prime. I'm using the wrong terminology. C and C prime, that if there's an intersection, let's say that this little yellow guy is an intersection. Let me zoom in on that. So this is C and C prime, and that little yellow edge is the intersection. Then what it's saying is that there exists a circuit contained in the union of the two original circuits subtracting away X. So the picture to sort of imagine is that we've got this. So the black stuff, the remaining black stuff is not there, but X is still there. X is the yellow element. And that's what basically is represented by this thing here. Okay, so that picture hopefully will allow you to remember this property C2, if you haven't, if you forgot it. So just remember this guy. Isn't this such a great picture? So, I don't know, what does it look like? Two bowling balls. No. I don't know what it looks like. Okay, so this is a fundamental theorem about circuits, and it's a theorem that defines the notion of a fundamental circuit. And there's a fundamental circuit associated with every independent set, and that's called the fundamental circuit associated with I and E. So basically, if you take an independent set and you add an element E, then I plus E contains at most one circuit, and it's called the fundamental circuit. So now it might not. It's not necessarily. It might still be independent, but if it's not independent, you haven't created more than one circuit. So to prove this, suppose to the contrary that by adding such an edge, there are two circuits that are so created. C1 and C2 are distinct, and they're both subsets of I plus E. Okay. So then, by using property C2 that we've just proven, we can take E, because we know that E there exists an E in the intersection of C1 and C2. We know that there has to be at least one E that lives in the intersection because we've created these two circuits by adding an E. And so that means that there exists the circuit C3 such that C3 is a subset of these two circuits except for E. And that's a subset of I. Okay. But now that's a contradiction, because now we're saying that there's a circuit here, C3, which is a subset of I, but by assumption I is an independent set. So therefore, this contradicts the definition of independence. So therefore, we're going to have a notation associated with this, and this is a crucial thing to understand, because there's going to be a polymatroidal generalization of this, which is going to, interestingly enough, be describable in terms of a lattice. But this is C I of comma E. I is the independent set, E is an element, and the polymatroidal generalization is going to say I is a vector inside of a polymatroid, and E is going to be a direction, and this is going to be so there's going to be a notion of a circuit in Rn, which is strangely enough, as you'll see. Okay, this is a fundamental circuit. So just pay attention to this, because it will appear again in future lectures. So we've got two matroids, and here's the algorithm idea. Actually, maybe we should take a brief break, because I forgot to take a break. So let's take a short break, and then we'll come back and do the algorithm idea. Okay, let's get started again. So let's start with these two matroids, which are defined on the same ground set, two independent sets. And the algorithmic idea, this augmenting This is going to be a generalization of what we saw for bipartite matching. But now, instead of what we're going to do is, instead of looking at bipartite matching, we're going to look at two arbitrary matroids. Okay. So keep in mind, if you want to sort of keep with the intuition that we did for bipartite matching, keep in mind the two matroids that are defined associated with a bipartite matching. But note that what we're doing here is not, we don't need it to be the case that these two matroids are partition matroids of a bipartite graph. They can be any matroid. So let's say that we start with some I that's in the intersection of the independent set. Okay, so that could be any edge, right? In the bipartite match, any edge is independent in both matroids, right? Because it's the case that in the two partitions that are set up, we are of size 1 in only one block of each of those two partitions. Now let's choose some. Now we're going to use matroid stuff. So let's choose some new element v1 that's not in the span of the current independent set with respect to the first matroid. So in the bipartite graph case, what would the span be? What would span 1 of I be? It would be all of the edges in the current block within which I lives on, say, the left side of the bipartite graph. Right? And if we choose some v1 that's not in the span, then when we add it to I, we have not lost independence in the first matroid. Why? Because we're not in the span. The only way the span is basically everything that when you add it to the current set doesn't increase the rank. And the not in the span means that the rank is increased by 1, and so therefore we're independent. So then, if it so happens to be the case that we're lucky, and say that I plus v1 is also independent in the second matroid, namely back in the bipartite matching case, if it happens to be the case that we're now touching a new vertex on the right-hand side as well of the bipartite graph, then v1, that one element, is now augmenting. Okay? And so what we can do is then we can augment I to become I plus v1, and we're still independent in both matroids, i.e. we're still matching in the bipartite graph case. So this is exactly a generalization, but now into the matrix case. Now what happens on the other hand? If it's the case now that we've added this v1 and we're independent in I1, but we get into trouble with respect to M2. So in other words, this is what we mean by getting into trouble with respect to M2, meaning that if we add v1 to I, we're no longer independent in matroid 2. Then thanks to the theorem, we know that we've created a circuit. We know we've created at most one circuit. In fact, we know we've created exactly one circuit because we know that we're no longer independent. So there's a fundamental circuit associated with this M2 that has been created. Right? And if it's the case that we remove an edge from that circuit, we'll be independent again in M2. Now if we remove v1 from the circuit, then we'll be independent. But we don't want to do that because that means it puts us back where we've started. But let's say maybe we can remove a different edge from that circuit in M2, or a different edge. I mean, it's a different element from the circuit in M2. In the case that we've recovered independence in M2, and then in fact we can do that. So let's choose some some v2 that's in this new circuit that's not equal to v1, and that means that this thing is going to be independent in M2. And why is that? It's essentially because when we've added v1 to I in matroid 2, that creates a unique circuit. We removed a v2 that's not equal to v1, and remember, any circuit is such that you remove any element and it's no longer a circuit, it's an independent set. And we've removed v1 that's not equal to v2, so therefore we've recovered independence and we haven't changed the span. Right? So the spanning set is the same. It's independent in M2. And moreover, if we move V2 from I plus V1, we're also independent in M1. Why is that?
Because V2 is in the circuit. Right? Because V2 is in the circuit.
No. Exactly. Because a subset of independent set is independent. So we could have removed anybody from there. So in other words, I mean, the circuit is associated with M2. And what we're doing is we're removing an element from the circuit, but in fact any element we could remove. I mean, I plus V1 is independent in M1. So any independent set, you can remove any element from an independent set. It's down monotone. It's subclusive, down closed. So it's the down closedness. So let me write that. Subclusive, which nobody uses as a word, but we use it because it's rare. We're going to populate the world with the word subclusive. In fact, there's only one paper that I've ever found that uses the word subclusive. And now we're using it. So anyway, so now what we do is we repeat. Okay, so now what has happened? So there's a problem, however, which is that we've added V1 to I, and so we've increased the span in Matroid 1. We've increased the rank, but now we've removed V2, and that kind of sucks because now we've gone back to where we started from. But we have recovered independence back in M2. But now let's find a new element, V3, that's in the residual span. So in other words, it's in the span, according to Matroid 1 of I, that's not in the span of what happens if we remove V2. Right? Because we don't remember, we've removed V2, but we want to still sort of recover what was added to I when we've added V1, and that will do that. Okay. So we recover what was lost here when we move it. So when we do that, then the span of I will be equal to span of I minus V2 plus V3. Right? Why is that? It's because of our choice of V3. Right? So we've chosen something that's not spanned, that's in the span of I, that's not spanned in the span of I plus V2. Now we know that also by removing V2 from I, since V2 is a member of I, we've reduced the rank. So we've lost something. We've lost a dimension. But now we're adding it back in when we add V3. And so we've got the same span here. And also, since the span is the same, if we add V1 to, say, this stuff, then it's going to be equal to the span of I plus V1 in Matroid 1. Okay. Why is that again? It's essentially because the span of 1, because I is essentially equally valuable to I minus V2 plus V3. And so when we add V1 to it, we've recovered it. And we're still independent in Matroid 1. So maybe, if we're lucky, by adding V3 now, which is a distinct element from V1, maybe we'll be somehow independent in Matroid 2, which would be really great. But on the other hand, it might not be. If it is great, then we've essentially got an augmenting sequence, right? If it's not, then we need to, if it's not, then we need to find some other element, C4, which is in the unique circuit, according to Matroid 2, that's created by adding V3 to I plus V2 minus V3 in Matroid 2. And we keep going back and forth, which is exactly, like I said, analogous to the bipartite graph case. In fact, it's exactly what we did in the bipartite graph case in terms of a matching, but now we're doing everything in terms of properties of the matroids, namely whether or not things are independent. So hopefully, eventually, we'll find an odd length sequence that will be, well, I should say, Yeah, so an odd length sequence such that if we do something with the current independence that we started from and S, namely take the symmetric difference, will be independent in both matroids. So let's use this blue, green, red encoding scheme like we did before for the bipartite matching. So basically what we're going to find when we construct such a sequence, we're going to have, I think I made a mistake here. I think it's supposed to be, sorry, I think this is supposed to be not equal, and this is supposed to be not in, and this is supposed to be in. So because the first one we chose was not a member of I. The second one we chose is I. The third one we chose is not an I, and we keep alternating before it. This is what happens when you do new bullet points. So then we replace I with the symmetric difference, right? And it's exactly analogous to the bipartite graph case, where we've got a matching, and then we take the augmenting sequence, and some of the edges, namely the green edges are new, the blue edges are old, and the red ones stay put. Okay, so the red ones are definitely correct. So the ones that are not involved in the augmenting sequence stay red. Okay. So here's an example. Now this is the example of two graphs that have, and unfortunately it's the same number of vertices, but you can see that it's a different vertex set. It's the same edge set for different vertices. In this particular example, what's different about the vertices is that it's the same number of vertices. It's the same number of edges. Namely, there are 8 edges, but they're in a very, very different configuration, and they're just named similarly. So, for example, like E8 here is the same as E8 here, while E7 here is E7 there, and so on and so forth, right? E2 there is E2 here. So you can see, for example, on the right-hand side, E2 and E8 create a cycle, but on the left-hand side, E2 and E8 are independent. So the sets of independent edges are different on the two matroids. Okay, so we start by essentially using the greedy algorithm, right? So we start off this thing by saying, okay, let's choose an E4. And you can see in both matroids, no circuit is created. Right? So red is essentially the current independent set. Okay, and then what we do is we choose another edge from something that's not in the current span of E4. So on the left-hand side, we're doing this relative to matroid 1. And let's say we got lucky, we chose E5. So definitely no circuit is created on the left-hand side matroid, on G1, right? And so we have these two guys. We have this one and this one. There's no cycle, so therefore it's independent. And on the right-hand matroid, we got lucky. So we had E4, which was the original edge, and we chose E5 there, and no cycle was created there. So we somehow, even though we chose E5 relative to matroid 1, we got lucky on the right-hand side in that no cycle was created. Everybody with me? Okay. So now, however, is there any additional edge we can add that won't create a cycle in both of the matroids? So let's try one. I mean, let's try, if we use our sort of geometric intuition, we might say, oh, look at E7, but that doesn't create a cycle on the left matroid, but it does create a cycle down there. What if we try, say, E8, but that creates a cycle there? And if we try, E2, that's going to create a cycle there. So that's basically all cases, because those are the only edges on the left that don't create a cycle. And so we've tried the only remaining edges on the left that don't create a cycle, and in all 3 cases, they've created a cycle on the right-hand side. So therefore, there's no additional single edge addition, just exactly like what we saw in the bipartite graph case. So there's no longer a single element addition that is independent in both matroids. So what do? Let's choose do this. Let's use this augmenting path algorithm. So let's choose E2. So there we are. There's E2, which is green, and we know that that doesn't create a cycle on the left because we've chosen it based on E minus the span of 1, right, of the current set. So E minus the span, what's up here, is definitely not going to create a cycle in Matroid 1, right? Because we're increasing the span. We're not taking something from the span of the independent set that we've already got. But on the other hand, as we checked, that's definitely going to create a cycle on Matroid 2, namely on the right-hand side, this down here. So we know that there must exist some unique circuit in Matroid 2 which was created. In fact, there it is. It's the green and blue circuit on the right. Here's the fundamental circuit in Matroid 2 that was created. And it turns out that the fundamental circuit, fundamental circuit is a subset of the independent set plus the new edge, right? So the independent set consists here on the right-hand side now. The independent set consists of the red and the blue, and the new edge consists of the green. And the fundamental circuit is a subset of the independent set plus E, right? Because the fundamental circuit does not include the red edge. So now what we're going to do is we're going to choose an E4, which is in that fundamental circuit. So E4 is this blue thing, is going to be the thing that we're going to remove. And the reason why we're removing it, the reason why it's blue is because that's what we're removing. And so we remove it, and then we choose E1 in the span to add, and then E1 is the green one. But we're lucky now, right? Which is that we're independent in Matroid 2, which is great. So therefore, if we, out with the blue and in with the green, if we do that, we're independent in both. This particular sequence, the augmenting sequence, was something that basically increased the size of the independent sets in both Matroids. Now the question is, are there any further augmenting sequences? So that's another exercise for you, problem set. Okay, and again, you can solve this anytime you want. You just search through the PDF files for the word exercise : and you will find all of the problems that will be on your problem set. Okay. So it's I is an intersection of two matroids. All right, so what does that mean? So this is sort of like a definition of what does an intersection mean. Either intersection means that I is in the intersection of the two independent sets of the matroids. And so we define this set S, which is a sequence of distinct elements, where if I is odd, we're in the member of the independent set. And if I is even, we're not a member of the independent set if I is odd, and we are a member of the independent set if I is even. And so let's go back to that thing. Remember this color-coded example? All right, so I think I was right in my typo fix there. This should be this. Okay. So we're going to say that S is an alternating sequence if the following is true. If the first addition is independent in I1, and if for all even I, the span according to Matroid true of this metric difference between I and SI. So SI is sort of the partial accumulation. SI is like you're creating essentially a chain of sets from this sequence. So this implies, therefore, that at every even point, if we take the symmetric difference, we're independent in Matroid 2. And also for every odd point, it's the case that we're now of rank 1 greater than we were originally, meaning that we've increased the rank by 1, or in other words, that if it's the same span as E1. So whatever we've added initially. So it's sort of like, this is sort of like a weird, greedy algorithm. So here's another intuition, what's going on. So we've chosen E1 without knowing the alternating sequence that's going to exist there afterwards. So while it might not be the case that we're allowed to keep E1 because the augmenting sequence, let's assuming that there is an augmenting sequence, it might not be the case that we can keep E1, but the dimensions span, the additional dimensions spanned by E1, whatever that is, we're going to be able to keep. Because if there exists an augmenting sequence, because when we get to the end, if there is an augmenting sequence, the size of S is going to be odd, the size of the sequence is going to be odd, and we're going to be independent in I2. So that means that since it's odd, I think I have this in the next slide. Oh, yeah. So since it's odd, I symmetric difference S is going to be 1 bigger than I. I think that's here, right? So the augmenting sequence is always going to be 1 such that when you take the symmetric difference with I, we're increasing the size of the independent set by 1. And so what this is saying, and getting back to this point I was saying a second ago, which is that the dimension span, thanks to this property, even though it's not really the greedy algorithm, it's sort of it's greedy with respect to the dimension that we've chosen, in the sense that if there's an augmenting sequence, I can choose any new dimension spanned by the first element I've chosen. So so it doesn't matter which dimension there is, as long as there's an augmenting sequence. So it is sort of semi-greedy. And I guess what I'm saying isn't necessarily going to even make sense yet until we sort of mention these theorems which we're about to say. So by finding the augmenting sequences, we can increase the size of the Matroid intersection until we stop. So we have these propositions, which we're not going to prove here, but basically it says that if there is an augmenting sequence, then the intersection is not maximum. Okay. So next, if the intersection is not maximum, then there exists an augmenting sequence. And the way that you do this is you construct this data structure called a border graph. And a border graph is itself a bipartite graph. So even though these are matroids, and they may not be graphic matroids, what one does is construct a sort of a data structure, which is the border graph, the border bipartite graph, which is basically a bipartite graph where left vertices are equal to the non-independent elements, the right vertices are equal to the independent elements, and Z is a set of edges which we have to define. So basically the set of edges Z, so we have left-going edges and right-going edges. So what we do is that for each, so we take I, and we look at the span of I in Matroid 1 except for I, and for every such E in the span of I in Matroid 1 except for I, we create a left-going edge from where the receiver is I, from all J that are in the fundamental circuit in Matroid 1 created by adding EI to I. So in other words, these left-going edges basically saying on the right-hand side we've got these elements, right, which when we add it to the independent set create a circuit, but then when we move left on the graph, it's basically telling us the thing that can be added. So interestingly enough, it's like the right-hand side gives us the things that can be removed from the fundamental circuit that's created by adding the things that that thing is being pointed, that thing is pointing to. And if it's the case that there is no such instance, in other words, if E is not in the span of I, then EI has an degree of 0. All right? And this essentially gives us all of the elements not in the independent set. Okay? And then moving to the right going edges is basically the opposite. It's like the same thing but for Matroid 2. It's basically saying that for all EI in the span of I, according to Matroid 2 except for I, you create this right going edge and you point it to all Cj that are in the fundamental circuit in Matroid 2 created by adding I, except for, of course, I. So I've got a picture that shows this, and there's the same thing. So here's the picture of what's going on. So here are the two graphic matroids that we saw, G1 and G2, and here for the current independent set, E4 and E5, which are edges in red. Here's the border graph. In the border graph, E2, E7, and E8 are sources, which are these guys. And E1, E3, E6 are sinks. Now the span of I except for I in Matroid 1 is E1, E3, E6, which are the sinks. And the span according to Matroid 2 except for I is E7, E2, E8, which are the sources. Okay? And so these are basically the right-hand side vertices, which consists only of E4. And this gives us, so basically we have edges coming from E4 to each of E1, E3, and E6. Okay, which is basically just the rules that we just saw on the previous page. And then we have right-going edges. According to this. And the theorem says that basically once we've constructed this graph based on this fundamental circuit, we look at the current independent sets, we construct the border graph, and we can just read off the augmenting sequences for free. So like E2, E4, E1 is an augmenting sequence. E1, E2, E4, E3 is an augmenting sequence, and E2, E4, E6. Each one of them is like E2, E4, and E1. It's an augmenting sequence. That's one that would basically increase independence in both of these matroids. But notice that again that this is the actual algebraic things have nothing necessarily to do with the graph. The algebraic stuff on the bottom is something that we can do for any matroid, not just the graphic matroids. The border graph, however, is something that you construct. It's a graph that sort of conveys properties of matroids, and it's actually something that we can visualize, even if it's the case that the matroids are not nicely graphic. And hopefully it's the case that it's clear that that in the bipartite graph, in the bipartite matching example that we saw, that this is exactly the bipartite matching. Now the question for you, the problem set, is to ask, are there any other augmenting sequences in this example? And you can look at that for your problem set. So let's just mention a couple of lemmas, which we're going to mention without proof. So if S is a source sink path in the border graph, and there's no shorter source sink path between the same source and sink, then S is an augmenting sequence. Okay? So we find longest source sink paths in the border graph. And if I and J are matroid intersections of M1 and M2 that have size difference of 1, then there exists a source sink path in the border graph according to the current state. Now, one thing to mention is that the border graph is dependent on the current independent set. For each independent set, you need to reconstruct the border graph. Okay, so it's not the same. You have to at every step you have to construct a border graph for doing this. If it's the case that we've got two intersections, again, of size difference 2, there are two intersections of matroid 1 and matroid 2, then there exists an augmenting sequence that moves us from one to the next. So in other words, it means that any two jointly independent sets of the two matroids that are different by size 2 means that in the border graph there is a source sink path that will move us from one to the other. It might move a lot of zigzagging back and forth, since the only thing we're asking for is size difference. But it exists. And then the sort of crucial theorem is that an intersection is of maximum cardinality if there are no augmenting sequences, or alternatively, if there are no source sink paths in the border path. And then the last theorem is that if for any intersection there exists a maximum cardinality intersection which is got span greater than both. So this is again this sort of greedy idea. Like we said, that we can sort of take any dimension to uniquely span, and that's okay, because we never need to remove existing span from a jointly independent set in both. And that's something that comes from the Matroid property. And all this stuff, of course, can be made to run in polynomial time, assuming oracle queries to the Matroid. Okay, so are there any questions? So that's basically the Matroid intersection problem, which shows you what you can do. The next thing we're going to define, which obviously we're not going to do today, is the Matroid partitioning problem. And that is a critical problem which, when solved, is going to give us a special case of submodular function minimization. So are there any questions?